This is take 3 now of it. So, a number called e, third day of exponentials and logs and all that fun stuff. So, today we're going to learn about a number. It's called e. Now, I draw your attention to the fact that this was discovered in the 17th and 18th centuries because today to discover the e number, we're going to use these fancy handheld things that could take us to the moon. Okay? We call them calculators. Side note, because I get distracted very often, did you know that the computer, or the processing unit inside the graphing calculators or inside your cell phones is more powerful than the computers that sent people to the moon in the 60s?
Really?
Yeah.
That's
That's actually true.
actually cool.
Yeah. It's pretty sweet that in your hand you hold something that could, if used right, send you to the moon. Okay? 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 Bang, zoom to the moon. Okay? So, we call E the natural base. Okay? Alright? I don't even want to know what's going on back there. Okay. Alright. So, what is E? Now, E was developed by a bunch of mathematicians who didn't have a lot to do back in the 17th and 18th centuries. Okay? And so, what they came up with was this cool number. And you'll see what the coolness about this number a little bit later on. So, let's consider the expression 1 plus 1 divided by n all to the nth power. Where have you seen that expression before? Where have you seen this 1 plus 1 over n to the nth power? Or, more importantly, I should say, what does it look like? You may not have seen it exactly like that. What does it look like? Nope. Compound interest is the one I was looking for. Yep. Because the percentage growth decay, that was p times 1 plus r, 1 minus r to the t power. Okay? So it looks kind of like compound interest. So let's use this formula here to figure out E. Okay? As we increase the value of n, this expression will get closer and closer to E as we go on. So let's plug 1 into that expression. So that's going to be 1 plus 1 divided by 1 to the 1 power, or to the first power. Okay? That one we can do in our head. Okay? 1 divided by 1, 1 plus 1, 2, 2 to the first power, 2. So this here is 2. Yes? Okay. Let's make n get bigger. So now we'll go up to 10. So that's going to be 1 plus 1 divided by 10 to the 10th power. Might need a calculator for this one. 1 divided by 10 is 0.1. 1 plus 1 is 1.1. 1.1 to the 10th power is... Let's go a little farther. Let's go 2.593742. Because I'm going to stop there because I ran out of space in my box. Okay? Yes? All right. Let's go to 100. 1 plus 1 divided by 100 to the 100th power. Okay? Now, while you're calculating that, I will say, calculating it more than once, like if this were my bank account, I'd rather have $2.59 than just $2. after the bank figures out the interest. You know what I mean? So that's pretty cool. Okay, so 1 divided by 100 is 0.01, plus 1 is 1.01, to the 100th power is, what did you get? 2.7048138. I'm running out of space, so I'm going to stop there. Okay. What's that next one? 100,000? 1 plus 1. Oh. So 1 divided by 100,000 plus 1 raised to the 100,000 power gets me 2.718262. Ooh, that's bad. I kind of muddled it in there. 2.718262. Yeah? Okay. Go one more. Which color didn't I use yet? Oh, black. Two point 718280469. Box is bigger. You can get them all in. Yeah? Okay. Now, if we were to go out to infinity, if I were to go out to infinity, then this would be, so E here is equal to 1 plus 1 divided by infinity to the infinity power. Can't do that on my calculator. Okay? So I just got to trust the fact that E is actually equal to 2.718281828459. Yes, ma'am. Huh? Yeah, buddy? Yeah, buddy. Okay? Now, the cool thing about E is that, yes, it is a number. But we can also treat it like a variable. Okay? Because it's a locked-in number. Okay? So all of our variable rules that we learned back in Algebra 1, and we went over again in Geometry, and we went over again in Algebra 2, and we went over again earlier this year in Algebra 3. I shouldn't say earlier this year. Earlier last year in Algebra 3. Just a single ha, that's it? Oh, aha. Okay? So, in this first one, I've got a base to a power times the same base to a power. What do I do with those powers? I add those powers. Yeah, sa. So that's going to be E, my base, to the 2x plus 5x minus 1 power. Well, what's 2x plus 5x minus 1? 7x minus 1. So this simplifies down to be E to the 7x minus 1 power. Okay? You now try the other three, knowing that you know how to do all of them. All right, so what do I do with that 3 and the 5 in that second one? Multiply those together right off the start, right? So that's going to be 15. And then I got e. And then what do I do with the exponents? Add them. So that's going to be negative x plus 5 minus 2x. So that's going to be 15 e to the 5 minus 3x power. I would also accept there 15e to the negative 3x plus 5 power. Okay? Those are one and the same. Okay? What about the 10 and the 5 in letter C? So they divide to be what? 2 top or bottom? Top. 2 on top. Okay. All right. So the 2 stays on the top. And what about the exponents then? We subtract them. So this is going to be x, my top exponent, minus my bottom exponent. And I'm going to leave that in a set of parentheses because I got to remember that I got to subtract both of them. Okay. So x minus x is 0 minus negative 3. Positive 3. So this becomes 2e to the positive 3 power. Fourth one, power to a power. What do I do in that case? Multiply those exponents. So this part here becomes e to the negative 6x squared, and that's still being multiplied by e to the x. Now I need to add those two. So that's going to be x plus negative 6x squared. So that I would write as e to the x minus 6x squared, or e to the negative 6x squared plus x power. Okay? Using your calculators that can take you bam zoom to the moon, okay, please calculate for me what e cubed is and what e to the negative 0.2 power is. So I got, if I type it into my calculator, I get a lot more decimals, right? Now, when I'm giving an answer, though, we could probably round to, I think I have it on your homework. Is it on your homework there, Hufflepuff? Is it on there at 3 decimal places?
Yeah.
Okay, 3 decimal places. So this one would be about 20.086, and this one would be 0.819 if we were giving it on the homework. Okay, rounded. But really, there's more to go along with it. Okay? Now, don't worry, fear not, there's no graphing tonight. Okay? Tonight. Okay? So I just wanted you to know, in this case, that I just wanted to show you the picture of an exponential growth and an exponential decay involving e. Okay? E is nice because it's logical. When we were dealing with exponential growth and exponential decay earlier this week, it was that whole, it's a growth if b is greater than 1, and it's a decay if b is between 0 and 1. And then I throw in those, that like number 4 and 5, or number 4 and 6 on the salmon colored sheet, where I throw in a negative b value, and you guys think it's exponential, but it's really not because there's conditions and blah, 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 blah. Okay? With e, that base is locked in. It's 2.7182880 something, 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 something. Okay? Right? It's locked in. So that doesn't change. The cool thing is that if the exponent is positive, it's a growth. And if the exponent is negative, it's a decay. It has nothing to do with the base because the base is Euler's number. It's got everything to do with the positive or negative of the exponent. is logical. You see a positive exponent, that's a growth. You see a negative exponent, that's a decay. All right? So here's the two graphs. An exponential growth on the left, an exponential decay on the right. So my question to you is this. Looking at the exponential growth and the exponential decay, what about the domain and what about the range? Domain. All real numbers. Didn't change. It's still an exponential function. So the domain is still all real numbers. What about the range? Y is greater than 0. Now, if we do some shifts on it, okay, then that would adjust that number. Okay? If we did a vertical shift on it, that would adjust that number, but that's just like the other ones. Okay? What about our horizontal asymptote? What is it? Y equals 0. What about our special points? 0, a still holds, right? Okay. In this particular case, it was 0, 1. Okay. What about 1? 1, what's it going to go through now? It's the fifth letter of the alphabet. E. It's going to go from 1, E. 2, E squared. Okay. Now, PERT, not just a shampoo. Okay? Alright? We can use, or we can bring into play now, because we're compounding infinite times, right? If we think back to how we developed E at the beginning of class, if we compound infinite times, that means that we are what's called continuously compounding. Okay? It's kind of like you're always living. It's not that your body just doesn't live in one moment, and then an hour later it lives again, and then an hour later it lives again, and so on and so forth. It's living the entire time. Okay? Banking. Your money is in your account. It's always earning you money in the bank. It's continuously being compounded. Okay? It's continuously being compounded. Okay? So we need to figure out what everything means. So in this function, or in PERT I should say, A stands for the amount of stuff. Sometimes it's going to be money. Sometimes it might be carbon-14 left in your body after you stop living. Okay? Sometimes it might be bacteria living in a petri dish. Okay? It's going to be stuff. That's your amount. P is going to be your initial amount. Your starting value. Okay, how many of the stuff you started with? E is E. R is going to be your rate. Once again, it'll be a percentage in the problem. You'll need to convert it to a decimal to use it in the function. But here's the cool thing about PERT. T. T is time. If time is given to you in minutes, then you use it in minutes. If time is given to you in hours, you use the same formula in hours. If time is given to you in decades, you're still good. It's whatever time frame your problem is, that's what the time is. It doesn't have to be in years, like in the compounded formula. Okay? All right? So, you deposit $1,000 in an account that pays you 6% interest compounded continuously. As soon as you see that word continuous, you're automatically thinking PERT. If it said compounded quarterly, then you're going back to that other one, that compound interest one. If it says continuous, thinking PERT. So this is an A equals PERT formula. Okay? So, what is my initial starting value? 1,000. So P is 1,000. E is E. What's my rate of growth? Not 1.06. Just 0.06. No. No. Okay. My rate is my rate. Okay. Now, because it's interest, that means it's growing. If this was decaying, then it would be negative 0.06. But because we're growing, it's just 0.06 to the t power. Okay? So, it says find the balance after 5 years. Well, A is going to equal 1,000 times E to the 0.06 times 5 power. What do we get? 1,000 E to the 0.06 times 5 power. And I get, now because we're in dollar bills, y'all, $1,349.86. Really, it's 0.858808 on my calculator, but because we're in dollars, we round to the cent. You now find me the balance after 15 years. So A here is equal to 1,000 E to the 0.06 times 15 there. Switch that to 15. And I get $2,459.60. Yes? Okay. Walk me through how to find the balance at, or when the balance will be $10,000. How would we do that? Well, let's use a graphing calculator, yes. Okay. Because we don't know how to do logs yet. Wink, wink, nudge, nudge, even though we've already learned them. Okay? So, walk me through it.
Alright, so what you're going to want to do is you're going to want to plug in your equation.
What's my equation?
1,000. Grab the 1. There you go. The E and then 0.06 T.
How about x?
Or X.
Because my function is of x.
Yeah, got that.
Okay?
Then you just kind of scroll up from there.
No.
No.
Even easier. I want to know when it's 10,000. So I put 10,000 in there. And it gets that. Now, I will tell you this, that if I had just started this problem, that would be what my graph looks like. Okay? But I got to scroll out to find where it is. So in the last class, what we did was we said x's is years, right? So we went -10 there. We went, sure we did. We went -10 there. We went, why are you doing this to me? Doesn't like me apparently today. We went 100 here. We went by tens there. We left that one there. That one we said it had to be above 10,000. And so we went by 1,000. And then here. And that got us to that. Ta-da! Okay? So with that being said, that means that when will my balance in that account be $10,000? In how many years? 38.4 years. Okay? Handle? Sweet. Forgot to go on the next slide. So today's worksheet is yellow.